Okay,
And
cool.
yeah.
Um, I I have one little thing I
Sure.
wanted to
Go
ask.
ahead. Mhm.
Oh, no, I was reading through some just online or stuff. What is Unity development like? Engine? Any like what make it special, or there are like a lot of development engines or things for robotics?
Mhm. So yeah, let me. I
Or
have briefly used Unity in the past.
Mhm,
It is like it is a simulation engine, um, and so when we talk about simulation, there are two parts to it. The first part is the physics of it, right? So when I say physics, it is basically kind of defining everything as though it's in real world. What I mean by that is, let's say you have a robot and you have like wheels attached to the robot, and then you're saying that the wheels can spin, and you have an arm, and you're saying that this arm is attached to this joint, and this joint can move linearly, or it's a prismatic joint, or like different types of joint, and you would say what the interaction force between them are. So those kind of things are basically physics. And when you define all those things, and then when you run the simulation, that's when you would see the magic happen. That's like when you say that, okay, let's move the robot or drive the robot. What happens? Things like things that happen in real world should happen in the simulator.
I see. Okay. So it's
So
a kind of simulator like Gazebo or in a
yeah,
sense,
well,
but deeper.
not yet, not yet. Hold on.
Okay.
So I'm just giving you the basics, right? So that's what a
So,
simulator should have. Like one component of a simulator is the physics engine, right? So the physics engine itself does not need any UI. Um,
hmm
it does not need any visual component, right? It's just math. You're just saying that defining these objects. If you've done engineering mechanics
hmm
in a college, you know that you just define things and then you just compute, like do the math, and then you get the answers, right? You don't need any visual components to it.
I
But
see.
for a complex robot, if you want to do things more productively, it will be nice, particularly for us humans, to have a visual component attached to that,
Okay.
right? So
hmm
that's the second piece of a simulator, which is not a must, but almost all simulators have that. And the visual component basically tells you, like when the physics says that there is a robot here, the visual component draws the robot in that particular place. And when the physics says that okay, the robot is moving, the visual component makes sure that the robot moves in the scene. So that's kind of like the two parts of a simulator. Okay.
I see. Okay. Okay. Yeah.
So
One
Gazebo
is the
itself.
background math, then other one is the visual space or
Yeah, you
okay.
can think of it that way. Yeah.
Okay.
And so when you think about Gazebo, Gazebo is more like a simulator where um, it has a physics engine and a visual component. And in fact, like the physics engine is itself is a separate component. That's kind of a physics. It's basically an math library, right? As I said, it's
hmm
just math, right? So it's just a math library.
Okay. Yeah.
So there are different physics engines. I think Gazebo uses the pi bullet, or no, the bullet physics engine. um, and okay, so that's the physics engine part of it, right? And then the visual component of it, on
hmm
Gazebo, it is not too polished. It's kind of like, it looks okay, but if you want to make it look like photorealistic, then you have to do a lot of work to make that happen. Like you have to texture the scene and everything.
Oh,
So
okay.
that's where tools like Unreal and Unity come into play. So
I see.
Unreal and
Oh,
Unity, these are not simulators per se. These are kind of game engines, in the sense that using those tools, you can create a game. So, so if you think about it, the question then is like, what is a game? Like, what is involved there? So in a game, you need to have physics, because if you have a character and you shoot the character and the character falls down, if it is not falling properly, like if it falls like a toy, you wouldn't get the feel of like playing like a real game. You want it to follow physics. Like our minds are um, uh, tuned so much to the physics. If you see things off, like if they are not following physics, it'll show off like right away.
I see. Okay.
So,
Yeah.
so what happens is that's where like these game engines started using physics in the background. Um, so you have this game engine, and then you have this physics engine that is running along with it. But for a game, they kind of like focus more on the visual component of it because that's kind of like what makes you more involved in the game.
Mm-hmm.
So they have a physics engine that kind of like details things, but since the visual component is the most important part, the physics engine kind of takes a backseat in the sense that in a game engine, you cannot let the math drag you. In the sense that when I shoot someone in a game, they have to fall down following physics in the sense with following gravity, right? If they
Uh-huh.
take a
Yeah.
long time to fall, it beats the purpose, right? It kind of like feel like unnatural, and you're like, okay, what's going on? So what is important is you need to have the math kind of calculated fast enough that it is real time. You know what
Oh,
I mean
wow.
by real time?
Uh, yeah, I mean, all the applicable laws of, I mean, physics, yeah, yeah.
Yeah. So what I mean by real time specifically is like if I'm saying that okay, I'm dropping something, it takes like half a second for it to hit the floor. Um, I can that's what my intuition would say. Okay, it's kind of half a second. But when you're calculating the physics, and some depending on how granular the physics engine is, it might take maybe half a second or maybe like 2 minutes to calculate the whole physics of it. From a physics engine perspective, it doesn't care like whether it's real time or not. It would just use the time that it used to calculate. But for a game engine, that is not the case. You want it to be as fast as the actual thing happening in the space. So when I say physics engine takes a backseat in the gaming engines, what really happens is they tune the physics so that it either gives the result fast enough that you can update the visual component to make it look real, or they bypass things, or they kind of like add heuristics to make it look faster. So they don't do the actual full physics all the time. Most of the time
Okay.
they do it, but sometimes they kind of like take shortcuts to get there because their primary thing is like real time, right? They wanted everything to be happening as though it's just like in time.
I see.
So Unreal and Unreal Engine and the Unity engines are basically these game engines. You can develop games with that. But people in simulation world, like robotic simulation, realize that, oh, these engines are really great because they have the physics engine integrated, but they also have the visual component really tuned in. Because I don't know if you work with texturing scenes or creating photorealistic scenes, it is
Mm,
really painful. It's
okay.
really painful because it takes a lot of effort to kind of like get things aligned and get things done. But then there's also a lot of knowledge and expertise that goes into making these skyboxes, making these images look real, the reflections look real. There's a lot of things in the background. So the game engines
I
have
see.
mastered
Wow.
that,
Okay.
like,
Yeah. I
right?
was not familiar.
Yeah, so the game engines mastered that like quite a bit. So the people in the simulation world are like, well, this is great. Like they have this thing mastered, and a lot of our robots have cameras, which means that we'll need photorealistic images to process. So particularly this happened when the drone revolution happened, right? Like a couple of years ago,
Oh,
uh,
okay.
when a lot of drones came in. The drones cannot carry lidars. It can just carry at that point. It can just carry cameras. So, but if you use if you simulate a drone in Gazebo, then the images that you get from the camera, simulated camera, is crappy, right? It's not like realistic. It's just like block world kind of thing. So people saw that, oh, Unreal Engine is great. So let's just use that. Let's just tune that to get to a simulation. So they kind of like transitioned to like took the Unreal Engine, wrote some wrappers around it, and they called it AirSim. I think that's one of the earliest kind of simulator that came out of a game engine and also got really famous. This was a couple
Okay.
of years ago. Um, and then and also like with all the computational advances, these things like the physics and everything caught up, right? Like if you have a really good processor, you could actually do the physics in real time. You don't have to wait for a long time, right? So that is also contributed to that effort. So eventually, what happened was these game engines got so good that you can do like anything with it. Like you can create a game, you can create a simulator, and all those things. So Unreal was one of those game engines. Unity is another one. They have these different. They have some like a little different architecture, but essentially these are game engines. So depending on what you need, and then there is also a difference in the licensing of how you do things. So Unreal, you can buy you can download it and just use it. But then when you build a game with it, I think there is you have to pay some royalty or something like that. And then Unity has something a little different. So
I
that's kind
see.
of like the background. Sorry, I could have answered you in one sentence,
No,
but
no,
I
no.
wanted to give you
Yeah,
the
you
background.
did background. Yeah, yeah. It has quite a bit history. Yeah,
Yeah.
how? Yeah, that's
Yeah,
great to know. Thank you.
yeah, sure. So but it's really fun to kind of like play with these game engines. And so on like at CMU, we kind of build the game engine for like use the game engine like the Unreal Engine to build a simulator for the moon rover, lunar rover that we are building. And it looks really like when you look at it, it's like, oh, is this like a video captured on the moon? It looks as real as that. And obviously, you can say that, okay, this is also looks a little gamey, um, but that's what we have been using to do a lot of testing for a robot. Like we used to
Mm-hmm.
have Gazebo simulator, and then we kind of transitioned and moved on to that to the
Okay.
Unreal simulator we wrote. So
So,
that's how good they are.
so sir, which is better, like Unity, Unreal Engine, or Gazebo, or Blender? Blender is also a simulation platform, right?
No, not necessarily. So Blender is mostly um, um,
Modeling software.
it's kind of an editor for like you can use that to okay. So it's okay, there are these all these tools, right? And then if you draw some like if you try to classify them, there is definitely some overlap, right? So Blender is mostly for creating it's for creating movies and things like that, right? They are there is more emphasis on the visual component. Like, so if you draw a graph and say, okay, visual component on the y-axis, and then visual accuracy on the y-axis, and then physics accuracy on the x-axis, Blender would be more along on the uh, top um, left corner. It's more towards visual component. Whereas you say like Unity or Unreal might be a little further down, a little more towards the right. So maybe let's try to draw something. Hold on. Whiteboard, new whiteboard. Okay, do you see my whiteboard?
Yes, sir.
Nice. Okay, so let's draw. Okay, draw a line. Yeah, let's say this is visual accuracy. Wow, it lets me do things like how you do in a PowerPoint. How this Grammarly thing. Okay, so if you just say like visual accuracy and physics accuracy, then let's just draw. Oh, this is too big. Okay, so Blender would be somewhere here, and you would say Unreal, and maybe the Unity or somewhere around here. I don't know which one. I think and Visual Unity might be a little better in the visual accuracy than Unreal, I guess. I'm not too sure. Need to check.
Okay.
And then you look at Gazebo, it is somewhere here, right?
Wow. Okay.
Oh.
Right. So this is kind of like I guess this gives you the picture, right? So Blender is more like it was developed for creating clips, movies, and things like that for like 3D movies, right? And then what happened was they also had to add physics to it because how good is a scene with a character that is not following physics? As I said, it 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 quickly gets like you
Noticed.
yeah,
Yes.
you quickly get it looks unreal. Like you like, oh my God, this doesn't look natural. And you start
Mm.
feeling that very soon. So that's why like any game engine or any movie kind of thing, it has to do this um, physics in it. So Blender, I think is also using Bullet, but I'm not sure. But that's not kind of a natural integration. I think you have to like integrate that into Blender to get your characters do the stuff, right? But it's like you can create like really complicated and really good kind of visual renderings and 3D models with that. So that's what Blender lies. And then Unity and Unreal, as I said, these are game engines, which kind of prioritize real-time action. So in Blender, so one other component I didn't talk about is the sometimes the visual accuracy can take much longer in the sense that um, I don't know if you guys heard about um, the rigs that Pixar had like in the 1990s when they first built the company. Um, so like even in the 2000s when they were having the whole movie generated, they would take like several minutes to render one frame of the movie. So let's say Toy Story, right? You have
Mm.
the different characters in there. They would have everything set up, and then they would send their computational rig to generate that frame, and it will take like let's say 10 minutes to generate one frame. And then for a movie, you need to have frames running at, let's say, 24 frames per second. And then for a 3 hour kind of like a movie, just imagine how many frames you have to spend and how many days or months you have to spend to generate that whole thing. So why it takes that long is because it kind of like uh, keeps refining the visual component, and that's why Toy Story was like or these movies look so real. Like it feels like, oh my God, it looks really good because they spend a lot of time kind of refining
Oh, got it.
the images. And part of it is like they actually one of the main things that takes a long time is the ray tracing part, where they shoot a ray from the screen from a pixel, and then they kind of like see where that ray lands. And then if that component has a reflective element, everything in real world has a reflective element to varying degree. So depending on that, that ray bounces off to another object that was close by, depending on the angle, and then that ray bounces off again. So they have to register everything. So let's say you have a mirror in a 3D world, and that's looking at each other. That's kind of like an infinite kind of back and forth thing, right? So that those are the things that they used to do, and it used to take a lot of time. And Blender was good at that. You cannot use Unity on Unreal for that because Blender is set up to have that photorealistic stuff. Okay. And then the game engines came in, and then the game engines were okay. We want visual accuracy, but we cannot spend all the time on there. We want physics accuracy, but we cannot spend all the time on that. All we care about is in that frame. So let's say you're running a game at 24 FPS, like 24 frames per second. So whatever time you have, um, let's see, if you have uh, 24, so in 1000 millisecond divided by 24, uh, so that is like 41 milliseconds is what you have to generate a frame, right? So you have to generate every frame within 41 milliseconds. And that's what these game engines prioritize. Okay, can we do the visual component within 41 milliseconds? And can we do the physics component within 41 milliseconds? If you cannot, then cut short the process, get whatever you have, and then let's use that.
So, sir,
Now,
what parameters are compromised in this?
so multiple things, right? So on the physics side of things, what you would do is you would so one of the major things that causes a lot of delay in physics engines is like you're trying to find the interaction between objects. So let's say you have a sphere and then you have another sphere that is kind of like hitting it. Based on the velocity and things like that, you would figure out what will happen, the velocity and the mass of the sphere. If one of the spheres is like really heavy, the other one is really light, and when it comes and hits the heavy sphere will not move. The lighter one would move away. But if they are the equal weights, then when you hit it, both of them would move away, right? So to simulate that in our head, it's like, okay, this is a simple thing, just two spheres. But then what you're trying to do in a physics engine is like you're actually looking at the mesh. A mesh is basically a set of vertices with triangle faces on them. So you're trying to see like where do they interact. And that interaction is kind of like a really hard problem to solve because there is nothing like a fixed surface. You're just having these triangle faces. You're seeing like where this triangle faces kind of like come into play. And so there is math, simple math to say that, okay, if this triangle face interacts with this triangle face, interacts, I mean like is crossing the other triangle face. You don't want them to cross because then you're saying that these objects are going into each other. Um, so the problem arises where when you have these things moving at different speeds, let's say if they are moving really slowly, then if you're in a physics engine, all you're doing is you're stepping through time. You're saying that at this instance, what is the physics looks like? At the next instance, let's say that next instance is 41 milliseconds. So what does that scene look like, right? You can make that 41 milliseconds, or you can make it half of it, like 20 milliseconds. So let's see what happens between these two. If you're moving really slow, 41 milliseconds, after 41 milliseconds, then it's kind of really close. That's okay. Then another 41 milliseconds, it's kind of close. But and then the next time step you might see like, okay, these are kind of interacting now. Now I should do stuff. But if you're doing like the 20 millisecond, then you spend a lot more time simulating this, right? So that kind of like makes the time longer. But why would you need 20 millisecond? Let's say these are moving really fast. Then um, at one instance, you would see that the objects are not touching each other. And the next instance, in that 20 millisecond, you might have actually gone past the other object, right? And then you're in trouble because now you're saying that these are two rigid bodies, but my physics says these are interacted or kind of like went into each other. What do I do? Right?
Right, right.
So that is kind of like a bigger problem. So what the real physics engines are like, if you have a physics engine that's kind of like looking into the accuracy, it would try to avoid that. So it'll say, okay, let me simulate it as slow as possible, or sorry, as fast as possible, so that I don't have these kind of problems. And then that way you can kind of figure out when the interaction happens and then act accordingly. Um, for gaming engines, you're like, okay, I don't really care about that. So when that happens, I will use some hacks. So when these objects went into together in physics, I know that, okay, that is gone past the time. So maybe I will say that these have already moved on, or some kind of hacks to kind of say that these are not interacted and or it just touched and kind of like things happening after that. So they use some hacks or heuristics to kind of like make it more make it look more real. So the same kind of thing happens on the visual side of things as well. Like I said, you use ray tracing, right? You take project a ray and you find the reflection, and then you see where that other reflection happens, and you can keep following that. One way you can kind of shorten this is you'll just set a threshold on how many ray reflections you would do. You would just say that, okay, I'll see where it interacts, and then I'll just look at one reflection. I'll not go beyond that. So these are the things that could actually exponentially increase or decrease your time. So let's say you say that I would do like 10 interactions, like 10 reflections. Now you have like a HD image, like 1080 p image. Then it is like at least a few 100,000 points in that image, right? So you have few 100,000 pixels, and for each pixel you find the reflection for, if you do it for 10 times, that's like exponentially larger, right? So now if you say that you just do it one time or two times, then it's kind of exponentially lower. So that's where the tuning or the parameters come into play. Does it make sense?
Yeah. Yes, yes, yes. Got it. Got
Okay,
it. Yeah.
cool. Okay, I saw Jishnu join. Hey, Jishnu.
Hey, how are you?
Good, good. How are you?
I'm good.
Good. So we're just talking about simulation and like the different physics engines and game engines and how they kind of like differ from each other.
Okay. I was just late by half an hour.
That's okay. It's a casual conversation anyway. So cool. So anything else? Do you guys have any other questions? Do you have any thing that you want me to explain on this going forward?
So, sir, in this, which would you like recommend learning? I am learning Unity right now,
Mm-hmm.
but I have seen my other robotist friends who usually do all the simulations on Gazebo.
Mm-hmm.
So, keeping in mind the robotics field, which is
Mm-hmm.
more useful in this?
Um, okay. So what I would suggest, the first thing, like, I mean, there is no like a common pill for any all problems, right? That doesn't work. That is not true. So the first question I would ask you is, um, what is your application? Like, which area are you working on?
Currently, I don't have a specific application as such.
Okay. So what's your specialization? Like, which? Okay,
From
let
a
me.
computer
Sorry, go
science
ahead.
background.
Sorry.
I have a computer science background.
Okay. No, that's okay. That's good. But what I'm asking is, let me clarify. Maybe the question is too vague. So let's say you're working on the drone side of things, or the perception side of things on a drone, right? So you say, so let's say you have you're building some drones and you're deploying in a field, and you're developing planning algorithms based on how, like, the perception from the drone, like the camera images that come in, right? um, so if that is the case, then I would suggest doing something like Unity or Unreal, because for those things you actually rely on the images from the camera, in this case simulated images from the camera, and if the images are not good enough, then it is not going to be like, you can still develop your algorithm and test them, but it's not going to be realistic, right? When you hit the real world, it's going to be completely different and your algorithms might fail. So if you're working on those kind of applications, then I would say go with Unity or Unreal. Um, let's say you're working on a mobile robot and you're trying to do the planning algorithm on that, but not based on the visual part of it. Maybe based on the lidar part of it, sensing. So in that case, Unity might be an overkill. In that case, a Gazebo simulator would be ideal, right? Because um, the other part is, like, if you're doing a lot of visual computing, you also need a lot of GPU cycles to do that. So in that case, you will take a simpler simulator like Gazebo and deal with that, and that should give you like good point cloud simulations, and then go with that. Um, but let's say you want to do something along the lines of um, a particle simulation. So for example, in one of our projects we were doing, we are trying to uh, design like wheels for a lunar rover. So if you look at the wheels, they have these struts in them, right? Like all the Mars rovers and the lunar rovers have this. They don't have the rubber tire, but they have this rim, and then they have these teeth on top of them that would grab onto the terrain. And we're trying to see like how many of these teeth you need to have, and how long they have to be, what shape they can be. So to do that, to test that, we actually have a sand bed, and then we kind of like see the interaction of these teeth with the sand, and then that's how we've been doing it in the past. And now we are transitioning to also doing that in simulation, where we simulate every particle of sand that interacts with this wheel. Okay. A couple of years ago, this was not even possible, just to be clear, because of the computation, the amount of computation you need to do. But now it's possible with all the GPUs and everything. There's also these libraries that are coming out that can do this kind of simulation. So if you're doing that kind of simulation, you care more about the physics than any visual component at all. Like these things don't particularly have a lot, like maybe like really trivial visual component to it. So if that's the case, then you would tend to go towards that. So it basically boils down to what you're trying to simulate, right?
Okay, yeah.
So that would decide which tool you would choose for your application.
Right, right, right. Got it. Got it.
Okay. So yeah, I think that's kind of like the bottom line. So which means that there is no one tool that you would learn and then you'll be done with it. You'll have to
Yeah.
keep learning new tools, but that's okay. The thing is like it's kind of cumulative. Like once you learn a tool, once you get the hang of it, you know that okay, these are kind of the major components in a simulator, right? And then when you get to use the next tool, you're just like, okay, I know these two. I've done this before, so maybe I can relate to this that the other concept, and then that's how you kind of like move faster.
Yes, yes. Right.
Okay, cool. Any other questions?
Not from my end. No.
Okay.
This graph is pretty good. Yeah, it helped me
Yeah, I think
realize. Yeah.
it's not complete. I think let me pull up what is the other simulator I was referring to. I'm kind of blanking out on the name. Actually, so the number of simulators out there is mind-blowing. There is a lot of simulators that are out there. And um, and more are coming out. So it's really impossible to kind of like keep track and learn all of them. Just pick the ones that you feel are good. So I would add what do you call the Isaac Sim somewhere here. So what you really want is a simulator that tends more towards this side, where you have both the visual accuracy and the physics accuracy. So
I
Isaac
see.
Sim is going in that direction, where they can actually do both the visual component and the physics component of it using GPUs, right? So it is tending in this direction. So is it so does that mean like learning Isaac Sim would be the end all be all thing? Probably not, because this also means that you need a beefy GPU computer to do most of the stuff. So some of the projects actually do not need that, and might not even have the resources to do that. So yeah, so you basically get to choose what you need to do, and as with anything in robotics or like in general in engineering, is it's always trade-off, right? You basically end up trading off something for something else. So so that's what it boils down to. So I'm trying to find what the other one is. Yeah, I cannot remember that. Maybe I'll send a Slack message once I kind of know that. Yeah, we've been using that simulator. That's the one which was doing all these simulating every sand particle. I think it's like simulating like 1 billion sand particle for like a wheel testing, which is kind of crazy now, but yeah. Cool. So, anything else that we should talk about? Jishnu, how about you? Like, how's your progress going on?
Yeah, it's been like I was mostly focusing on the exams tomorrow.
Oh, nice, nice. Good luck.
Thank you. I have one doubt. Like, where does
Okay.
this Arvis or Folksclo comes in? Like, how it's different from these simulators kind of things?
Arvis?
Arvis and Folks Folksclo.
Oh, Foxglove. Okay. So they don't fit into this graph at all. So Arvis and Foxglove are just viewers. They don't actually do any simulation, right? So if you have a robot in a simulation in a Gazebo world, then you can look at the robot in Arvis or Foxglove, like see where that robot is. But they don't do any simulation by themselves.
Okay, it's like those things are just for viewing what links are there, what the links and joins are doing.
Yeah, they're basically showing you whatever the simulator says it is, or whatever the real world says it is, right? So if you have a robot in simulation, you need a simulator in the background to simulate it in the first place, like a Gazebo or a Unity based or a Unreal based simulator. And then the Foxglove or Arvis would come into play and they would just show you what it is. Or if you have a real arm in the world, then Arvis or Foxglove can show you what that arm is and what the um, what the angle and all those things are. But they don't have any physics engine in the background to kind of simulate it.
Okay, got it.
Okay, cool. Okay, cool. If that's it, I think we can end a little early. I'll give you like 15 more minutes of your time. And we'll we'll talk to you guys next week then.
Thank you.
Okay.
Have a good day ahead, guys. Yeah.
Yep.
Bye.
Thank you.
Yeah, bye guys.
Yep. See you guys.
Thank
Bye.